Today is we are covering the last section here. There we go. Review on Monday. Test 2A is on Tuesday. Test 2B is on Wednesday. There are reviews for both of those online right now, so if you go to the website, you can look at those. There are some uh, calculus quizzes that you can take, like do you remember all these rules and stuff like that. There are quizzes for each one of those, or kind of like fill in the blank. You can kind of quiz yourself, and then there are answers to each one of those. And in class on Monday, we'll do as many problems as we can as far as finding derivatives and stuff like that. If we don't get done, remind me, and I will email you, or I'll post a copy of the solutions to 2A, so you can look at all those and see how to find the derivatives of each one. And then as far as 2B goes, remember that's going to be basic derivatives, and then do you know what to do with them? So could you find a tangent line? Could you find a linearization like we talked about yesterday and come up with an approximation? Can you solve related rate problems? If I gave you a position function and asked you questions about its velocity or its acceleration or when it reached its highest point or when it was moving left, right, speeding up, slowing down, could you do that sort of thing? Okay. So Tuesday is just finding derivatives, and then Wednesday is can you find a derivative that's of medium difficulty, and then do you know what to do with the derivative once you find it? Okay, do you know how to use it to solve problems? Okay, so make sure between now and Monday you've downloaded those reviews, you've looked at them, you know what questions you have, so we can address those on Monday. Okay, all right. So this last section is on something called hyperbolic functions. Sometimes you'll hear them called hyperbolic trig functions, and we may be able to see why. We're just going to cover the basics. We're going to do some relatively simple problems, even though these are going to look kind of weird. Hopefully they're fairly easy. If you're interested in knowing more about these, I have a degree in math and I have a master's degree in math, and I've only used them just they were introduced in a calculus class just like this. And then I never saw them again. If you go into engineering or something like that, then you'd probably see these more frequently. Okay, so if you're interested in where these come from and why they do what they do, we'll explore that just a little bit. But there is a reason why they sometimes are referred to as hyperbolic trig functions, and there's a good reason why they're called hyperbolic functions. Khan Academy has some really good videos and some explanations. You could get a good flavor for it, investigating and watching videos. Probably in less than a half an hour, you could get a pretty good handle on it. So the first thing we're going to start with is just two very simple differentiation problems. So, these could be on the test on Tuesday or on Wednesday. You could have something like this. We probably wouldn't call them hyperbolic functions, but if we were going to find the derivative here, the first thing you might want to think of is, well, let's slide that 1/2 out front. Let's use that constant multiple rule. So we're not thinking of each one of these as a fraction. And then we'll find the derivative of, this is just e to the x minus e to the negative x. Well, finding the derivative of each one of those is pretty easy. That would just be e to the x. And what would negative e to the negative x be when I find its derivative? Yep, it's going to be positive e to the negative x. And then I've got this 1/2 out front here. So if I were to write it in this single fraction format that we had to begin with, it would be e to the x plus e to the negative x all over 2. And that would be the derivative of that first function right there. Okay? Easy enough? Yeah. Very good. So let's take a good look at this. You'll notice that what we've got here is a very similar function. Imagine sliding that 1/2 out front. I'm going to find the derivative of e to the x, which is going to be e to the x. And then I'm going to find the derivative of e to the negative x, which is going to be negative e to the negative x. And then I'm going to have the 2 on the bottom. So as Juan was pointing out, what do these two things have to do with each other? What do these two functions right here have to do with each other? They're derivatives of each other. Okay, so if you take the derivative of one, you get exactly the other. And if you take the derivative of the other, you get exactly the same as the first one. Okay? So these functions are extremely useful, and we're going to run through a definition for each one of these. They're called hyperbolic functions, and again, we could spend half an hour investigating why they're called this and stuff like that. They're actually quite useful, but this is the definition and how they're pronounced. So this is called And there's disagreement about how you ought to pronounce these, okay? So this is the way I learned it. You could find people that say it slightly differently, but most of them we agree on. So this would be called the sinh. Some people say sine h of x or something like that. H, again, representing the hyperbolic. So we'd say sinh of x is defined this way. It's e to the x minus e to the negative x all over 2. So we're taking two exponential functions, combining them together through subtraction, and then dividing by 2. And then we're doing the same thing for this one. Okay, I pronounce this one as cosh. Okay, so this is the sinh, this is the cosh. You might hear people call it the cosh or something like that. Doesn't really matter. The point is it's the hyperbolic cosine function. Okay. Okay. Like Oshkosh. Okay. And that one, again, is an exponential plus another exponential divided by 2. So again, the only difference between these two is one is a minus, the other one is a plus. Okay? And if you think about how sine and cosine, like when you were in trig, more often than not, cosine had pluses in it and sines had minuses in it. Okay? So, I mean, I don't care how you keep it straight, but those are the definitions. Okay? And then the cool part about this is this stuff should sound pretty familiar. So if I were to do this one, which tanh is how we'd pronounce that. Okay, it's going to be the sinh over the cosh, which would be, well, let's think about this. If I did this fraction over this fraction, would I ever divide by a fraction? No, I'd flip this one over and I multiply. If I flip that one over and I multiply it, so let me change colors. I'll erase this in just a second. I'd put a 2 on the top, e to the x plus e to the negative x on the bottom. The 2's are going to cancel. So here's how we could define this in terms of exponentials. It's going to be e to the x minus e to the negative x over e to the x plus e to the negative x. Okay? But it's the sinh over the cosh. Do you want to take a guess at what the, well, let's see, how do we pronounce this one? If we say this one's sinh, cosinh, okay, so that would be the cosinh. Guess how it's defined? It's the reciprocal of the sinh. So it would be 2 over e to the x minus e to the negative x. Okay, if this is, well, let's see. Oh, cosinh. No, I said that incorrectly. We actually pronounce this cosech. Yeah, sorry about that. Okay, and yep. Okay. Yeah, and this one is the sech, okay? And it would be the reciprocal of the cosine, so it's going to be 2 over e to the x plus e to the negative x. Oops, I should write that 1 over cosh. So 1 over the cosh is the sech. And then what about, this? So this would be cotangent. Cotangent. So it's going to be the cosh over the sinh. So it's going to be just the reciprocal of this guy up here. So it's going to be e to the x plus e to the negative x over e to the x minus e to the negative x. Any questions? I know that's pretty wild. Okay. We'll just take those definitions for what they are. Okay. So, yeah. Got it? Okay. All right. So let's do something really easy. And at this point, other than that starter question, all we've done is just some pre-calculus ideas. They're defined in terms of exponential functions. So let's find the sinh of 0. To find the sinh of 0, I'm literally going to plug in a 0 right here and a 0 right here. So this is going to be e to the 0 minus e to the minus 0 over 2. And this is a 1 minus a 1. So I get a 0 on the top and a 2 on the bottom. So the answer is 0. So if you plug a 0 into the sinh function, into the hyperbolic sine function, you end up with a 0. What if you plug in a 0 into the hyperbolic cosine function? You do. because this is going to be e to the 0 plus e to the minus 0 all over 2. That's a 1 plus a 1 all over 2, so you end up with 1. You want to, what? Not really. Not really. Okay. They call these hyperbolic trig functions sometimes because they're so closely related. There are so many identities that are involved here that are very similar to the trig functions and their identities, but they don't really have anything to do with them. Okay. We just call them that because of the similarities, not because there's anything trig involved here. Okay. It is kind of interesting that that happens, though. Okay. So what's this going to be? It's going to be 0, okay? Because if it's going to be the sinh over the cosh, it's going to be 0 over 1, so that's going to be 0. Any questions there? Okay, so you have some problems that are literally that easy. All you have to do is find the value of a hyperbolic function, okay? So then you've got some problems where they want you to verify some identities. And if you remember from trig, that may or may not have been the funnest thing on the planet, verifying identities. Okay, and here's what they're asking us to do. So we want to verify that if I take the cosh, subtract the sinh, I get e to the negative x. Well, normally we pick the hardest side to work on, so let's change these two into their exponential definitions. So this is going to be e to the x plus e to the negative x all over 2 minus, this is e to the x minus e to the negative x all over 2. And we want to see if we can make it equal e to the negative x. Well, let's take this and let's do a couple things with it. Let's break apart the fractions. Okay? Or I suppose if we had a common denominator, you could do it that way. So this would be e to the x over 2 plus e to the negative x over 2. This is minus e to the x over 2. And this would be plus e to the negative x over 2. Those two cancel. I have 2 of these, so that means I have 2 e to the negative x over 2, which is e to the negative x. And there we go. Yeah. Yeah, and that's okay. If you want to just treat them as a common denominator and multiply through, distribute the negative, that would be fine. Okay, which side do you want to work on here? Work on the right side, looks a little more complicated. Okay, let's see what we've got here. Remember, occasionally when you're verifying an identity, you have to work on both sides. Let's see if we can avoid that to some extent. So here's what we've got. If I take the cosh squared, that's going to be e to the x plus e to the negative x over 2, quantity squared, plus e to the x minus e to the negative x over 2, quantity squared. And let's see what we've got here. If I square this binomial and square the denominator, so I'm going to have a 4 on the bottom of each one of these. And if I square the binomial, I get this. I get e to the x squared. What's the easiest way to write e to the x squared? E to the 2x. Okay? This would end with e to the negative 2x. And what do I get when I multiply the two of these together? E to the x times e to the negative x is going to be, remember, same base, add the exponents, that's going to be e to the 0, so that's going to be a 1. So when I multiply them together, I get a 1. But remember, I'm going to have 2 of those, so I double that, so that middle term is going to be a 2. Any questions there? If we've got that figured out, then this one ought to be pretty easy. This is going to be e to the 2x. This is going to be plus e to the negative 2x. And then when I multiply the two of these together, one of these now is negative. So I slide that negative out front. The answer to that would be negative. So when I multiply these together, I get negative 1. Double that, I get minus 2. Is that correct? So now I'm just going to do this. Okay, to save space, I'm going to put these over one single fraction bar. Okay, and it was addition, so I don't have to be too terribly careful. So I'm going to get, let's see, 2 minus 2, those go away. And I have 2 of these guys here, so I have 2e to the 2x's. And I have 2 of these guys right here, so I have plus 2e to the negative 2x's. And that's all over 4. Which if I factor out a 2 and cancel, I get this. I get e to the 2x plus e to the negative 2x all over 2. Does that look familiar? What was plugged into these exponentials? 2x, okay? And by definition, that's what this would be. Okay, any questions there? Okay, so a lot of this assignment, I've looked through it, there aren't that many problems to do. A lot of this assignment is just kind of getting you used to how these functions work, reminding you of how we can use some algebra and some trig ideas in order to verify some of these identities, okay? And then we'll do a little bit of calculus, not a ton, and we'll look at the graphs and we'll figure out a little bit more about how these functions behave. So it says if you look at those starter questions, the functions that were derivatives of each other, you'll notice that the first one could be written this way because by definition that is what the sinh function is. That's the hyperbolic sine function, e to the x minus e to the negative x all over 2. Well, if I find the derivative of that, I end up with this right here. I end up with this other function right here. Well, by definition, what is that? Okay, its derivative is e to the x minus, or excuse me, plus e to the negative x all over 2, which is the hyperbolic cosine. So the derivative of sinh is cosh. The derivative of the hyperbolic sine function is the hyperbolic cosine function. Derivative of sine is cosine. Another similarity there. So the derivative of the sinh function is cosh of x. Well, now here's where it's a little bit different. What was the derivative of this right here? E to the x minus e to the negative x all over 2, right? So it was the sinh. How does that differ from the trig functions? It's not negative, okay? So this is sinh of x. So normally when we found the derivative of cosine, we ended up with negative sign. Not the case here. It's not negative. It's still positive, okay? Let's see. If you had to guess what the derivative of tanh is. What's the derivative of cotangent? Secant squared, okay? The derivative of this is the sec squared of x. All of these are positive, okay? All of these are negative. So the derivatives of those regular 3 trig functions that we're used to working with, they're hyperbolic analogies, if you will. They're all positive, okay? And the reciprocal ones are all negative. So for this one right here, let's think about it. If it was cosecant, what would it be? Derivative of cosecant is cosecant cotangent, right? So its hyperbolic equivalent would be negative cosec cotang. Normally this would be secant tangent or sec tanh. What did I say about all these? They're all negative, okay? And cotang, cosec squared, negative in front of it. So the trig functions we usually like working with, sine, cosine, tangent, or their hyperbolic similarities here. Sinh, cosh, and tanh, all positive. Okay, any of the reciprocal ones that we're used to working with, they are all negative. Okay, so if you'll go ahead and flip the page over. Okay, these are diagrams from your textbook. Again, if you wanted to look at these a little more closely, how they make the shapes they do and stuff like that, it really is quite interesting, and you can find lots of videos on the internet. We're going to take a look at the sinh, cosh, and the tanh, and we're going to look at them from the perspective of we're going to add those exponentials together and see what we get. So we're going to zoom in on the sinh function, and what I've got here is half of e to the x, and I've got half of, minus 1/2 of e to the negative x, okay? So this is the negative exponential if you flip it over and horizontally reflect it. So vertically and horizontally flip it, okay? So if I take this function and add it to this function right here, if I add this value and this value together, they're symmetric. They're equally above and below the x-axis, so I end up with a 0. That's why the sinh of 0 was 0, okay? And then if I consider this function over on this end, has some asymptotic behavior. It gets closer and closer to 0. So it doesn't have that much impact on the overall shape, but this one is increasing exponentially. So if I take this one that's increasing exponentially and add or subtract something that's getting close to 0, it continues going up. So it kind of acts like an exponential growth over here, okay? On the other side, this one tends toward 0. This one tends toward negative infinity or exponential growth in the negative direction. So on this side, this one takes over. So we've kind of got an exponential curve here, kind of a mix of the two in between, and then we've got an exponential curve here. So exponential growth in the positive direction, exponential growth in the negative direction. In the middle, they kind of cancel each other out, and that's why we hit 0. Make sense? Okay. So this, just to make sure we're clear, this graph right here, that is the sinh function. Okay, and it continues going up and out, okay, down and out. Okay, so the domain would be all real numbers, and so would the range. Okay. Let's take a look at the cosh function. Okay, that's going to be the sum of e to the negative x. Okay, a function that's a little easier to figure out than negative 1/2 e to the negative x. Okay, again, that would just be a vertical flip of this, a reflection across the y-axis. Okay, so we've got this exponential decay here. We've got this exponential growth here. Again, we're just taking the exponential function and multiplying it by half, vertically shrinking it by a factor of 1/2. Okay. And at this point right here, both of them have a value of 1/2. So when I add the two of them together, I get 1. When I come out here and I add these two functions together, again, I've got this exponential function that's coming down, getting closer and closer to 0. So this one is the one that dominates the shape. So if I take this exponential curve right here and I add something that's getting close to 0, it still grows exponentially. Okay? Same thing on the other side. So the cosh looks like this. Okay. Now, some people look at that and they're tempted to say, oh, well, that kind of looks like a parabola. It is not a parabola. Okay. It is not a parabola. Okay. Looks like one. Okay. We'll talk about that in just a second. Okay. Okay. Because that shape does have a name. Okay. And if we think about what happens if we take, so this would be e to the x minus e to the negative x over e to the x plus e to the negative x. And we thought about, well, what would happen if I took this value right here and put it over that one there? These are both tending toward positive infinity. And they're made out of the same functions. So if I took a ratio of this point over this point as they're getting larger and larger, the top and bottom get really close to the same number. That's why out on this end, we have an asymptote at positive 1. Okay? And on the bottom, they get really close to the same number, but they're opposites of each other, so we get close to negative 1. Okay? Now, I realize that's not enough explanation to say, oh, I know exactly how these functions work. Okay? We don't have time for that in this course. That's not what this course is for. All we're doing is just introducing them, getting you used to the basics. Okay? So, let's talk about an interesting application because this is by far the most famous one. Anybody been to St. Louis? Oh, you got to go to St. Louis. If you get a chance to go to St. Louis, it's a pretty cool city. And there's this thing right here, okay? It's called the Jefferson National Expansion Memorial, or in other words, what's it commonly called? Gateway Arch, okay? So it's usually called the Gateway Arch, okay? And anybody that knows anything about math looks at this and says, that looks like an upside down parabola, okay? It's close, but not quite, okay? They are different shapes and they have different properties, okay? It's called a catenary, okay? And this is an inverted catenary, okay? And a catenary is the shape that you get, and this is one reason why engineers use these. If you were to hang a wire, like if you go out and look at telephone poles and power lines that are strung between each other, if you have a heavy wire that's strung between two supporting points, that path, that little shape right there is called a catenary, and it can be described using a hyperbolic cosine. Okay? So one tiny interesting application of those. Okay? Nope. You'd use exponentials instead of power functions to describe it. Okay? All right. So the last thing we're going to do, looks like we're doing great on time here, is we're going to figure out some of these limits analytically if we can, and then we're going to confirm some of them graphically. Okay, so I've got pictures up here that I'm going to keep off the screen on purpose, and I'd appreciate it if you didn't look up there to figure out what the limits are. Okay, we're going to figure them out analytically, and then if we need to look at the graph to kind of confirm that, let's go ahead and do that. So let's do this first one right here. So we want to figure out, we'll pay attention here because it changes from infinity to 0 to infinity, and then I think the last one is 0 from the positive side. So let's think about what this would be and how we'd figure this out analytically using those techniques that we learned in Chapter 2. So remember, limits don't go away in this class, and they don't go away when you take 1220 either. Okay? Limits always come back to haunt you if you don't get them figured out. So this would be the limit as x approaches infinity. This is e to the x minus e to the negative x, e to the x plus e to the negative x. So, as x approaches infinity, what happens to this right here? Closer and closer to 0. Okay? What happens to this one right here? Closer and closer to 0. Okay? So, when we're tending toward positive infinity, which of these two terms has the most effect on the shape? That one right there. And same thing on the bottom. So even though this goes to, and I mean overall this goes to infinity and that goes to infinity, the important part here would be this behaves like e to the x over e to the x when I'm plugging in large number. Does everybody agree with that? This is exactly the same term on the top to start with as it is on the bottom to start with. So the top behaves like e to the x and the bottom behaves like e to the x. So what would I end up with as in a limit as x approaches infinity? Positive 1. This one's a little bit easier. This one's the limit as x approaches 0, e to the x minus e to the negative x all over 2. What does this one turn into? Careful. That one turns into a 1 minus a 1 over 2, 0 over 2. Answer's 0. Okay? Now, let's slide up here and take a look at this. We were finding the limit as x approaches 0. Again, a two-sided limit. It approaches 0 from this side and 0 from that side. So that's graphic confirmation of that one. And we were interested in the limit as x goes to positive infinity. Okay, remember, we said this has an asymptote out here at 1. Okay, and we just confirmed that both graphically and analytically. Okay, any questions there? Okay, let's do the next one graphically. Let's look at it and then let's confirm it algebraically or analytically. The next one is the limit for the cosh function as x goes to positive infinity, right? What's the answer going to be? Positive infinity. Okay, let's come down here and let's take a look and see if we can confirm this. So this would be the limit as x approaches infinity. The definition is e to the x plus e to the negative x all over 2. What does this part tend toward? This one tends toward infinity. What about this part? 0 all over 2. The top's tending toward infinity. The bottom is a finite number. So the limit is infinity. That's going to increase without bound. Dividing it by 2 isn't going to change the fact that it increases without bound. So our limit's going to be positive infinity. Okay. No graph for this one. At least not one that's at the top of the page. So let's think about this for just a second. Think about what this would be from the definition. The definition of this is it's 1 over the cosh function. So it's going to be the limit as x approaches infinity. This is going to be, 2 on the top. And this is going to be e to the x plus e to the negative x. Well, how is this one related to this guy over here? It's just the reciprocal, right? So on this one, we're going to have top is a 2. Nothing we can do about that. Okay. The bottom is tending toward positive infinity. What happens if you have a finite number and you're dividing by something that's getting bigger and bigger and bigger and bigger? Overall limit's going to be 0. Okay. Okay. Another one that we don't have a picture for. So let's think about what the definition would be for this. So we're going to have the limit as x approaches 0 from the positive side. This one's going to require a little bit of thought. Okay, cotang. That means we've got cosine over sine. That means we've got the plus thing on the top, the minus thing on the bottom. So we've got e to the x plus, plus e to the negative x, e to the x minus e to the negative x. And maybe let's see what happens here if we plug in numbers that are really close to 0. Okay, really small numbers on the positive side. All right. So if I plug in a number really close to 0, what do I get out of this? Something that's getting really close to 1. What do I get out of this? Something that's also getting really close to 1, right? So what's the numerator getting really close to? It's getting really close to 2. Okay, are there any questions about that? That's the easy part here. Sure? I mean, this is done just like the other ones. The issue is going to come up right here. Okay, what's this one approaching? That one's approaching 1. What's this one approaching? Also approaching 1, but now there's a minus in between these. So we need to be a little bit more clever about this. The issue is not the top. Does everybody agree that the top is getting closer and closer to 2? Okay, so I'm going to change this just slightly, and here's what we're going to say. The top is positive, and it's getting really close to 2. Isn't that right? Top's always going to be positive. I'm taking 2 positive quantities and adding them together, so it's always going to be positive. This is getting close to 1, and that's getting close to 1, so the top's going to get close to positive 2. You with me there? Okay, now think really carefully about the bottom. It's getting close to 1, but if I plugged in a number like 0.1, plug 0.1 into the exponential function. What is e to the 0.1? 1 point something, right? It's a little bit bigger than 1, okay? So I'm going to represent that this way. I'm going to say, just for instance, this is going to get close to 1, but it's getting close to 1 from above. Okay, think about what the exponential function looks like. It looks like this. I'm grabbing a number that's a little bit bigger than 1. Yeah, it's getting close to 1, okay, but it's getting close to 1 from above. So it's a little bit bigger than 1. Confirm that on the calculator, right? Okay, everybody okay with that? Okay, think about this one right here. E to the negative x looks like this. I'm grabbing that number right there. So yes, it's getting close to 1, but it's a little bit smaller than 1. So this would be like subtracting 0.9. Now remember, just a second ago we said the bottom was approaching 0, right? Or approaching 1 minus 1. Okay, so the top is positive and approaching 2. Remember doing this in chapter 2? Is the bottom positive or negative? It's positive. And if I take two numbers that are approaching 1 and I subtract them, what are they getting close to? They're getting close to 0. Okay? So if the top is positive and the bottom is positive, the answer's got to be positive, the limit's got to be positive. And if I have a finite number divided by something that's getting closer and closer to 0, what's the overall limit? Overall limit is infinity. Okay? Good? Question? Okay. Okay, what we're saying is the value is approaching 1. Okay, so notice on our graph right here, we're approaching 0. 0 is right there. What are these function values approaching? They're getting closer and closer to 1. That's what we're talking about. Don't mix the x value with the y value. Got it? Okay. All right, come up here for just a second. And I think we should be able to make rough sketches of what the reciprocals of each one of these look like. So if I took this graph right here, and let's say down below, I wanted to graph the coset. Okay, these are huge positive numbers. Okay, what's the reciprocal of a huge positive number? Tiny positive number. Okay. Pick the number 4,000. What's the reciprocal of 4,000? 1/4000. Okay, so all of these values right here, I'll highlight them, from about here up to there, their reciprocals are going to be tiny positive numbers. Okay, so we're going to get things like this. These numbers right here, these are very small positive numbers. What's the reciprocal of a very small positive number? A very large positive number. Okay? So the reciprocal of these small positive numbers is a very large positive number. And what's the reciprocal of 0? Undefined. Okay? And the same thing happens here. Okay? So we're going to get a shape that looks roughly like that. So the coset function looks kind of like, it's not, but it looks kind of like a hyperbola. At least I'm pretty darn sure it's not a hyperbola. Okay? Let's talk about this guy right here. What's the reciprocal of the cosh function? The sech function. What's the reciprocal of 1? 1. What's the reciprocal of, let's say this number's 2. What's the reciprocal of 2? 1/2. The bigger they get, the smaller their reciprocal. So it does something like this. And it does the same thing on both sides. You can see that that's an even function. What's the reciprocal of all these numbers out here that are really close to 1? What's the reciprocal of 1? 1. Okay, so this runs along a horizontal asymptote, and then these are small positive numbers. It goes like this. We have a horizontal asymptote of y equals 1, and then the same thing happens over here. Okay, something like that. So that would be the cotangent function. Again, just rough sketches, just the idea behind what the graphs would have to look like. Okay, and then let's look down below. We were finding the limit as x approaches 0 on the cotangent function. Does it approach positive infinity? Yes, it does. Okay, all right. And again, I want to point one more thing out from the graph. Do you notice anything about the the sinh function and the tangent function as far as derivatives are concerned? Similar in what way? Yes. Okay. But let's just look at these. Aren't these always positive? And aren't these always positive? Okay. These slopes would be negative, 0, and positive, right? negative, 0, and positive. Okay, so you can kind of see how they're related through derivatives. Is that all right? What about these slopes? Again, always positive. Big slopes, yeah, like maybe 1 or exactly 1, and then positives again. Big positive slopes, 0, and then big positive slopes. So you can kind of see from the graphs that they are derivatives of each other. Okay? Whereas with the trig functions, you have to throw that negative in there when you're finding the derivative of cosine. Okay, any questions? Okay, let's run through and do a couple of these. You have a few problems where they do actually ask you to do some calculus, so they want you to find some derivatives. So we want to find the derivative of cosh evaluated at 0. Well, you should know what that is, right? Wouldn't that be the sinh evaluated at 0? So what should the answer be? Should be 0, okay? Because this would be the sinh of x evaluated at 0. And you could do it using the exponential definitions if you needed to. Let's take a look at this one right here. So we want to find y prime if y is x times the sinh of x minus the cosh of x. Nasty? Maybe. What rule applies here? Product rule. Got to use the product rule here. So y prime is going to be the first times the derivative of the second, so that's going to be the cosh of x, plus the second times the derivative of the first, so that's going to be the sinh of x times 1, minus the derivative of cosh, which is sinh. And it doesn't ask us to evaluate that or anything, it just asks us to find it, so there it is right there. Okay? Any questions? Oh, well, yeah, what do you know? Didn't even notice that. What do we have? Oh, they cancel each other out. Awesome. Nope. Okay, so let's take a look at this last one. This last one's kind of interesting. This, if I remember correctly, this is a good review of some of the algebra skills that we need. This is why this is a good question. So we're going to have the cosh of ln x, and I want to find the derivative of that. What rule? Chain rule. Okay, so that means f prime is going to be derivative of the outside, so that's going to be the sinh of ln x. So found the derivative of the outside, left the inside alone, and then I'm going to times by the derivative of the inside, and the derivative of the inside is 1 over x. Okay, now this wouldn't be too bad, but let's think about how the sinh is defined. It's defined in terms of exponential base e, and exponential base e has something to do with an ln. So let's see if we plug that in there into the definition of the sinh function, if we can simplify this. So this would be e to the ln of x, well that looks good, minus e to the minus ln of x, all over 2 times 1 over x. And now we'll stare at that for a minute. Because part of that is very easy. And then another part is maybe not so easy. Okay, what part's easy? What do these two make? Yeah, they're inverses of each other, so that's going to make an x. So I've got an x. This is a 2. What do these two make? Just a positive x? Careful. So here's what I want to know. Okay? Don't worry about the negative in front. Tell me what e to the negative ln of x is. What is it? Juan's got it. It's x to the negative 1. In order to allow these to undo each other, I need to slide that negative out of there. So here's what we do. We write this as e to the ln of x to the negative 1. Now they can undo each other, so I have a minus x to the negative 1. Good there? Any questions? Okay. Then we times that by 1 over x. So this is going to be x minus 1 over x over 2 times 1 over x. I don't, however you simplify it, it doesn't matter to me. So I would do this. I would do x squared minus 1 over x over 2x. Is that okay? We'll flip that over and multiply. So this would be 1 over 2x. So this is going to be x squared minus x over 2x squared. Does that look okay? Any questions? Yeah.
So flipping to the other page, example 2b.